Hey, good morning again, team. Chemistry coach coming at you. Time for a new journey today into the realm of the atom. The atom, not the superhero, the atom, who's real popular now. The atom and atomic theory. So more of an introduction to it. We're really going to hit this hard later, much later, in one of the later chapters. But we got to get through all this matter stuff first. But let's get kind of where this idea first came from, and I'm not going to go through 20 minutes of gory historical details for you. I'll give you maybe a minute or two. But this is fun stuff if you're bored on a Saturday morning and want to look into some cool, interesting history. I took a whole class at UCI. It was the history of chemistry. It was fascinating. Don't remember much. That was like 30 years ago. But it was kind of neat. You take all the math out and you get to know, we just throw these names at you, but in a regular semester, we just don't have time, in a 16-week semester or 18 or whatever length of your semester, or even quarters are. There's a quarter system at UCI when I taught there. It just goes by so fast. So there's so many things you got to get through. There's not enough time. And so a lot of the great history just gets swept under the carpet. And you're like, what can you do? So anyway, this concept of the atom a lot of times starts with John Dalton and Dalton's atomic theory, which we're going to get to. Most people kind of start it there, but really it has its origins way back in the philosophy, the fantastic glorified philosophy days of those Greek philosophers, right? So if I mention Plato or Aristotle, you're like, oh yeah, I know those names, or even Socrates. You're like, oh, Socrates, Bill and Ted's Excellent Adventure, Socrates, man, and Twinkies and Genghis Khan. No, we're not going to go Bill and Ted's Excellent Adventure, although time traveling back to meet these people would be absolutely fantastic. You would just blow their minds. Keanu Reeves rocks. So if I said Plato and Aristotle, you're probably like, oh yeah, two of the greatest ever. If I say Democritus, you'd be like, oh, who's that? Well, unfortunately, history kind of got screwed for a long time as far as science is concerned, because there was kind of this battle of what matter was philosophically. They didn't do experiments back then, right? So they're going, what is matter? And there was a battle between Democritus, who obviously got swept under the rug of history, and Aristotle with their views of nature and matter. Democritus looked at it from his atomos or an atomic point of view. So really its origins come from him and his mentor, Crippus or so. I get these names mixed up. But anyway, he gets most of the credit. We're talking way back, give or take 400 BC, somewhere around that time. And imagine, the way I look at it, imagine you're standing, we're in Southern California. You head over to Laguna Beach or something like that. And you stand up on a hill or dune and you're looking far away at the beach. It looks like one substance, right? You can't see the grains of sand. So it looks continuous, doesn't it? But if you get closer and get down on the beach and you grab a handful, you can see the grains of sand and stuff. You're like, oh, interesting. But from that point of view, what if you're so far away, there's tinier particles in there, right? And you're so far away, it looks continuous in that grain of sand, but maybe if you could see close enough, there'd be tiny particles of sand in that grain of sand. And if you get closer down, you could see particles within those particles. Well, how far could you theoretically go until you get the absolute smallest particle size of matter? And that's what he called the atom, Democritus. Turns out he was pretty much right, but history changed that. Plato did not like him at all, right? That's a bummer when one of the greatest philosophers doesn't like you very much. So, nobody's going to listen to him anymore. Bye-bye, Democritus. And Aristotle's view of matter was completely different. He has the one that was accepted for the next 1,000+ years of matters being a mix of the elements air, earth, water, fire. Well, you couldn't be more wrong on that one. And unfortunately, Democritus got swept under the rug of history for over 2,000 years. It wasn't until John Dalton, which we're going to do next, kind of resurrected that based on some actual quantitative measurements. So we're going to have to introduce some how quantitative science was kind of introduced and some of the key characters in that and what caused John Dalton to resurrect this idea of the atom. Let's get into that. So much cool history I can't talk about. I'm so sorry. You can look it up yourself. Alrighty then. So let's fast forward a couple millennia. Right, I'm going to skip a lot of cool history. We're going to jump straight from the philosophy of the atom, from the ancient Greeks, Democritus, to the scientific theory of the atom based on actual evidence and data. Remember, Democritus didn't have access to the techniques we have today in lab. They didn't know what a lab was. All right. So we're talking by 1808, developed over several years, probably about over 4 or 5 years or something like that. But by about 1808, John Dalton was able to condense all of his ideas into several postulates. That was called Dalton's atomic theory in time. So he converted the atomic philosophy of Democritus into the scientific proposal. Of course, we know that now as Dalton's atomic theory. Not the greatest laboratory guy. I think he was colorblind, actually. So you might hear some colorblind is called Daltonism sometimes. That's just an interesting little side note there. So these postulates or statements were made to try to explain some incredibly key and critical experiments that led to laws, some of the most important laws of science. Law of conservation of mass being one of them, law of constant composition. These were hugely important in understanding matter. Of course, there's conservation of energy, but we're talking just matter at this point. So what we're going to do is we're going to take some time to go through just 2 of these critically important laws. What they were about couldn't be explained at the time, right? Just that's a scientific method right there. You can observe something and we can quantify things and run things in lab. Doesn't mean you understand what's going on, right? We have to propose a hypothesis, which hopefully becomes a theory and all that fun stuff. Go watch the scientific theory video. But let's list out a couple of those experiments and then which develop into laws and how that poked and prodded John Dalton to propose the scientific theory of the atom to try to explain those laws. You'll see kind of the interplay between, observations and theory and how it all comes through, how we understand things in science. It's a fun little game. The first of these key experiments or laws that John Dalton was trying to explain happened in 1774, law of conservation of mass. Big deal by one of the biggest brains in history. I don't speak French, but Antoine Lavoisier, I don't know. Well, anyway, Paris, France. This guy, you could claim Antoine Lavoisier was the most important scientist on the planet during that time. You could support that as a pretty valid claim. He was the one to really explain combustion. It was while he was doing combustion studies. He's the one to really figure out that oxygen was in air as an element, and he named it. Who named oxygen? I think he named hydrogen too. It's hello, is that important? It's a lot of people consider him the father of modern chemistry, right? He put it was into the starting the metric system originally. I think he had some impact on that. Lists of modern elements at the time. Just truly phenomenal what this person did. A lot of people think of him as one of the first ones to really quantify science in general, to go from this qualitative outlook to a quantitative one with really good laboratories, equipment, like an analytical chemist bent, right? Key thing. So he was able to collect some really good data. So he was testing some stuff, the phlogiston theory. He kind of, disproved the phlogiston theory. If you want to look that up, this really whacked out theory. But he was doing some studies, and he looked at a chemical reaction, which is reactants going to products, right? You mix some stuff, and you form some stuff. Pretty straightforward. And he found that when he was able to accurately, quantitatively measure the total mass of all of his reactants, right? In this case, some combustion stuff. He could measure the total mass of the products as well. And he found out that they were always the same. Didn't really matter what reaction he was doing. They were always the same. He goes, isn't that interesting? Wasn't thinking about atoms at the time. And another way of stating that is that matter, whatever matter was at the time, couldn't be created or destroyed in a chemical reaction, right? Didn't mean he could explain it. That's just what he noticed. And that was the law of conservation of mass in a very simplified form. Unfortunately, Lavoisier, it's just the mob idea, right? We're talking French Revolutionary times, right? So I think he invested in some kind of program that allowed to get taxes to the royal government. And in the revolution, if you had any ties to that, you were in trouble. So Lavoisier and some of the investors in this, I don't know what it was, some company or something, Farmers General or something like that. Don't quote me on that one. They all got rounded up, couldn't defend themselves, and the mob guillotined them all. Shink. There goes probably the top scientific brain in the world. So sorry. For nothing is amazing. Of course, later they went, oops, put a statue up to him. So sorry, we, put science back by 100 years. Right. Let's look at another big law that was a huge, huge deal in this era, right, in the late 18th century. And then that instigated Dalton into proposing his atomic theory. Joseph Proust. Remember that name. This isn't too long after Antoine Lavoisier, right? A lot happened in the 1770s. So 1779, Joseph Proust doing some studies with some chemicals and compounds. And imagine taking a compound, which, they didn't necessarily even know at this point was elements mixed together, or truly be able to comprehend it at that time. But if say I had a compound consisting of two elements, if I could separate those elements and measure the masses of the individual elements, I could take one divided by the other and get the mass ratio, or the percent composition by mass, or some way of quantitatively looking at how much is there of this element versus how much is there of that element. And what Joseph Proust found in his studies was that the mass ratio of elements in a compound was constant. It was always the same, regardless of the source of that compound. It didn't matter where you got it, how it was made. If you broke down the elements into the mass and took the ratio of those, it was constant. Always, always, always the same. He couldn't explain why. Right? Didn't know about atoms and stuff at the time. But that's what we call it. And sometimes you'll see it as the law of definite proportions as well. Law of constant composition. So all samples of a compound are the same composition. That's kind of a bland kind of way of looking at it. I like it more this way, where the mass ratio of elements in a compound are always the same regardless of their source. For example, if we took water, now they didn't know water was 2 atoms of hydrogen, 1 atom of oxygen. They did not know this at the time, all right? But if you took water and broke it up into hydrogen and oxygen, maybe via electrolysis or something, collect the hydrogen, collect the oxygen, you could find out that oxygen is about 88.81% oxygen by mass and about 11.19% hydrogen by mass. Or if you actually measured those values and took the ratio, took the mass of oxygen divided by the mass of hydrogen, you'd get about an 8-to-1 ratio. So water is always an 8-to-1 ratio of mass of oxygen to hydrogen. He couldn't explain why. It's just something he found. And he goes, wow, okay. So now we're going to take a look at these two, law of constant composition, law of conservation of mass, and what provoked John Dalton to propose these postulates of Dalton's atomic theory to try to explain these. And follow the story with me and see if you can nod your head with me and go, that proposal makes sense because it explains this law. All right, so a few decades go by and John Dalton comes on stage left. One thing, it doesn't have to do with Dalton's atomic theory or anything like that, but just kind of, I'm a big history buff. I love reading history. You look at the law of conservation of mass, 1774, law of constant composition, 1779, right? French Revolution happening around that time. Well, what else? There was another revolution going on. 1776-ish to 1781. Oh, the American Revolution. Interesting. And who was one of the key people, other than George Washington? There's a lot of key people, but my favorite historical character is Benjamin Franklin, who our Continental Congress sent over to where? France, right? To try to recruit their aid into getting America, to beat Britain, right? England. Kind of interesting. So I haven't read the details of this yet, but I'd like to, is the relationship between Joseph Proust, law of constant composition, and Benjamin Franklin. Benjamin Franklin, of course, being a worldly renowned scientist. the connections happen, right? What a fascinating time to go back to. If I could have a time machine, go back in the late 1700s and meet all these amazing characters, what they were thinking. But anyway, that's beside the point. Down the rabbit trail, back we come. Come on, woo, back we go. All right, Dalton's atomic theory. So again, this was 1808-ish. Right, so a bit later. Here's a list of the postulates that John Dalton stated. First one, what is an atom? So this is resurrecting that atomic philosophy of Democritus. So matter consists of atoms, right? The Tomos theory, which are the smallest indivisible particles of matter. They cannot be created or destroyed, right? And we could add in there that smallest indivisible particles that retain chemical identity today, because we know, of course, they contain subatomic particles, but they didn't know that at the time. And then he also proposed that all atoms of an element are identical. Pretty valid proposal at the time. Turns out that's not so true. He didn't know about isotopes. And then atoms of different elements obviously would be different. So lead atoms are totally different masses, different, all these than sodium atoms, right? Pretty simple, but all sodium atoms are the same. Again, make a little note of that one. That's an incorrect statement. It's not incorrect. It's not completely true. Didn't know about isotopes at the time. So let's look at, I ran out of board space. Let's look at some of the other postulates that now help us explain the law of conservation of mass and the law of constant composition. These are key. This next proposal is key. Since he was able to propose this idea of this indivisible particle that can't be created or destroyed, right? Well, couldn't these indivisible particles called atoms of one element be combined chemically with these indivisible particles of another element to create these compounds, right? But if you can't break an atom apart, right, these atoms retain their identity, they must only combine in specific integer ratios. You can't have half an atom or a third of an atom, right? So they have to combine in integer ratios, very specific integer ratios, in order to explain the law of constant composition. Right? For example, if we have water with a constant, we looked at it, constant mass ratio of about 8:1, or the percent composition by mass is always the same for oxygen to hydrogen, but the ratio is about 8:1 oxygen, hydrogen by mass. Well, if two atoms of hydrogen always combine with one atom of oxygen to give this unique substance called water, H2O, he's the first one to propose this stuff. Wouldn't it make sense that if it's always that exact same atom ratio, and if the atoms always have the same mass, right, then the mass ratio of oxygen and hydrogen must be constant, regardless of where you get the water from. It has to be constant. Makes sense. So he was able to explain the law of constant composition just by this proposal that atoms combine in specific integer ratios. Yeah, it turns out later there's some weird things that don't quite obey this, right? But if you want to take more advanced chemistry, off you go. There's some crazy substances out there. Let's look at one more. And different people will, some people teach 3 postulates and combine, and 1 and 4 together, whatever it is. I just like to list out his idea of the atom. What is an atom? They're different for different elements and the same for the same element. How he explains the law of constant composition, and then how he explains the law of conservation of mass. So I like to put it into 4, just me. So if you learned it in 5 postulates or 3 from a different professor, whatever, it's really not that important as long as you get the main ideas. Let's do the last one. All right, his last main postulate, in some form of this, right? You'll hear it explained different ways, but a chemical reaction is just a rearrangement of atoms. Remember, atoms can't be destroyed or created, right? You can't have new ones popping out of nowhere. You can't have one just disappear into nowhere, right? So would it make sense that the total number of atoms that you're starting with in a chemical reaction of each element will be the same both before and after a reaction? It's like you got 2 dancing couples and you just switch partners. Right? You create new combinations and maybe they dance a little bit differently, but the people don't change. The atoms do not change. You're just recombining them, rearranging them. And when you get new combinations with specific integer ratios, you create new substances with new chemical and physical properties, right? That's how you can explain a chemical reaction. And you could take that extension that if the total number of atoms of each element is the same before and after the reaction, that means the total mass before and after the chemical reaction must also be the same, because you got the same number of atoms of each element. That never alters. You're just recombining them. So the total masses must be the same before and after. That explains the law of conservation of mass. It seems so wonderfully simplistic, doesn't it? But, took some heat for it, man. It took a while for this to gel with the science community. This, your atoms, you're so stupid. Even people with PhDs can be immature sometimes, right? Especially if you've been trying to, if you've been believing one thing for maybe 30 years of your life, and then somebody comes up and says, you're totally wrong. Your view of matter is completely wrong. You tend to have issues with that and try to defend yourself, even if you're wrong. All right, so it took a while for this to breach its way into the general science population. But makes total sense to us, I think. So this led to one new proposal, and I'll end it with that. All right, there was something that you put their brains in a tizzy for a little while. I don't know what a tizzy is, but you get the idea. It messed them up a little bit. Because it was found that there were some elements that can combine to create compounds that had different mass ratios. Remember, the law of constant composition said that the compounds always had, elements would combine to form compounds that had the same mass ratio. But hydrogen and oxygen, carbon and oxygen, nitrogen and oxygen seems to be part of the problem all the time, right? Could combine and create compounds that had different mass ratios of elements. And so it took atomic theory to help explain that, because what you could get from atomic theory is if atoms combine in specific integer ratios, well, maybe there's some elements that there could be multiple specific integer ratios that it could combine to form, which would then create compounds with different element mass ratios, right? For example, right, water versus hydrogen peroxide. You're aware of those. So water is a 2 hydrogen to 1 oxygen ratio. Hydrogen peroxide is a 2 to 2 ratio. Well, can you see that the mass ratio of oxygen to hydrogen would be higher, right, in one versus the other, right? You've got, 2 atoms of oxygen here and 2 atoms of hydrogen, and here you have 1 atom of oxygen and 2 atoms of hydrogen, right? If you calculated the mass ratios, they're going to be different. Doesn't matter what they are specifically, they're going to be different. They had a hard time wrapping their brain around that until Dalton's atomic theory. One of my absolute favorite chemical compounds, right? N2O, laughing gas, versus NO2, which is that kind of the brownish orange gas you see in smog, right? This has 2 nitrogens to 1 oxygen. This has 1 nitrogen to 2 oxygens. It's flipped backwards. Of course, they're going to have incredibly different mass ratios of the elements. Hard to explain until Dalton's atomic theory came around. So law of multiple proportions, right? Carbon monoxide versus carbon dioxide creates other issues. So really helped out a lot to explain things that people have been running into. I think that's enough theory for now. Let's get into the realm of physicists now. Because if somebody proposes, what do you think? If somebody proposes the existence of an atom, but no one's ever seen one, wouldn't it be cool? Well, monumentally, world-changingly historic to be the first person to actually see an atom or prove the existence experimentally of an atom. You would go down in the realms of immortality and science, and this is where the physicists come into play. Next video.